So now I want to discuss convergence rates of quadrature rules and a result that seems to be not completely known in the literature on uncertainty quantification, and it's surprisingly also a rather recent result. So this is from a 2012 paper, which deals with the convergence rates as quadrature rules. And why am I saying that this is not that widely appreciated in the uncertainty quantification literature? So you might say that, generalized polynomial chaos is great because it has, exponential spectral convergence, but I'm going to show you that quadrature rules actually have the same convergence order. Yeah, so it's so-called Clenshaw-Curtis rule and also Gauss quadrature. So we have a closer look at Clenshaw-Curtis, which we have seen for sparse grids. At Clenshaw-Curtis, going to abbreviate CC quadrature rules. Which have the following notes, which are nested, right? So you remember ZK is the cosine of k minus 1 over n minus 1 pi, which are the extrema of the Chebyshev polynomials. And well, Clenshaw-Curtis is constructed as exact for polynomials up to degree n minus 1. Yeah, so it has n nodes, so it's easy to have it exact for polynomials up to degree n minus 1. I just interpolate the function, so the polynomial at these n nodes, and integrate. That's the quadrature rule. All right, and well, this is related to Chebyshev polynomials. So the key to the following thing, the following arguments is given a function g, defined on minus 1, 1 with values in R. We expand it in Chebyshev polynomials. Which is g of z, sum m equals 0 to infinity, am tm of z. So t are the Chebyshev polynomials, am are the expansion coefficients, and we use that these expansion coefficients have a certain decay rate, which follows from our notion of smoothness. So it's smooth in the sense that am decays like m to the minus s, and that's related to, some kind of differentiability of order s, which I'm not going to make precise. It's a little bit technical, but we say for short that g is in xs. Okay, well, and here's the lemma. Should actually be a theorem, but in the original paper it was a lemma, I think. So g in xs, and then the error en of g of an endpoint CC quadrature rule behaves as this. So en of g is the error, so that's true integral qg minus q endpoint cc g, and that's less than or equal to constant depending on g times n to the minus s. So again, the convergence order is just given by the smoothness. So where the constant depends on G and its derivatives. All right, so before we prove this, again, the main point of this result, under suitable smoothness assumptions, this means that Clenshaw-Curtis quadrature rules show spectral convergence. So infinitely fast. Assumptions CC shows spectral convergence. And well, a similar statement is true for Gauss quadrature. I'm not going to prove this to you, but it's in the original paper. True for Gauss quadrature, which also shows spectral convergence. All right, so not every quadrature rule has spectral convergence, but two famous ones and two building blocks of other quadrature rules. Remember the sparse grids that we constructed based on Clenshaw-Curtis. So I want to prove this to you, and the proof is nice by itself. It works like this. So Clenshaw-Curtis is exact for polynomials up to order up to degree n minus 1. Thus, when I do the following thing, I express the error as, well, I can expand my function in terms of Chebyshev polynomials, and then I just need to apply the error to every Chebyshev polynomial. So maybe this is a bit fast. I assume that I'm expanding my function, right? Then I apply my quadrature rule, and I subtract the real integral from it. And for each of these terms, if this is a polynomial of up to degree n minus 1, the error is 0. Yeah, so I get this formula here that I've written down, that the error of G is actually a sum of the higher order expansion coefficients and the error of integrating the higher order Chebyshev polynomials. And if I want, I can estimate this as some m running from n to infinity, absolute value of am, and en of tm. Yeah, so the error of the endpoint quadrature rule when integrating the mth Chebyshev polynomial. All right, well, I can say something already. So furthermore, all odd terms in the sum vanish, because in this case, both the true integral and the integral using the endpoint quadrature rule is both 0. Yeah, because the Clenshaw-Curtis nodes are actually symmetric. All right, so therefore, let m be even. From now on. And now, well, I've defined aliasing for you. We're actually going to use it. Yeah, so that this quadrature rule with endpoints cannot tell the Chebyshev polynomial of order m apart from higher order Chebyshev polynomials. And I'm going to explain this. So we now actively use aliasing. So we take this representation of the m. So think of m as being large. So then I can divide it by with a remainder, and I can divide it by n minus 1. I get that this is 2j, so this is because m is even, and I get 2 times a remainder. Yeah, all multiplied by 2 because this is all even. Yeah, so division with a remainder, which means that minus n minus 2 less than or equal to r less than or equal to n minus 1. Yeah, so it's actually the remainder which is bounded here. And now what does aliasing do precisely? So we have this formula for the Chebyshev polynomials, which is cosine m, missing the z here, m arc cosine of z, and zk is cosine k minus 1 n minus 1 pi. Well, we have the following property. Tm of zk is the same as T2r of zk. So why is that the case? I take the mth order Chebyshev polynomial, right? And then I have that I can divide the m into a 2jn minus 1 plus 2r. And so imagine I put now, let me write this down, because Tm of zk is T 2j n minus 1 plus 2r of zk. So that's actually cosine of 2j n minus 1 plus 2r applied to cosine, applied to r cosine of cosine. Yeah, so actually to k minus 1 n minus 1 pi. Yeah, so there's an r cosine, but there's hit with the cosine, so I have this in here. And now I see that this is a cosine of 2j times k minus 1 pi plus 2r k minus 1 n minus 1 pi. And you see that the first term is now a multiple of 2 pi, so it doesn't matter at all. Yeah, so this is the same as the cosine of 2r k minus 1 a minus 1 pi. And actually for the cosine, it doesn't matter what sign r has. So I can say that this is 2 absolute value of r zk here. Yeah, so I've proven this aliasing property. Now what I can say this, so since Clancho-Curtis is exact up to degree n minus 1, we obtain that if I take the endpoint Clancho-Curtis quadrature rule and apply to Tm, this is the same as QCCN as T2R. Because of what we've just said, right? The quadrature rule cannot tell the mth and the 2rth Chebyshev polynomial apart. And well, this is now a polynomial that it can integrate exactly. So here I can write QT2R. So it's the real integral here. And that means that the error can be expanded by exact integrals of Chebyshev polynomials, which can then be computed. So the error can be expanded by exact integrals of the Chebyshev polynomials. Oops. So that looks like this. So I have En of Tm. That's the term that's interesting. So what's the error when integrating the nth order Chebyshev polynomial? So this is true integral minus Clancho-Curtis integral. We know now that this is true integral minus true integral of the 2rth. Yeah, so This is the true integral, and actually I can write this down. So you hopefully believe me. If not, do it as an exercise. This is the true integral of the mth Chebyshev polynomial. Is the true integral of the 2rth Chebyshev polynomial. And well, I can rearrange this so it looks like this. So it's 2 4r squared minus 1 minus 2 m squared minus 1. All right, and I mean, what's left is to estimate all of these terms. And that's a bit tedious, so let's do it without further ado. So we know that m is bigger than or equal to n because all the other terms are integrated anyway. We know that 1 over m squared minus 1, the denominator in the second term, behaves like n to the minus 2, right? Or I can estimate it like this. So that means if I take the error when integrating g, I know that this is bounded by this, the n of tm. And then we can write this as a constant 1, j from 1 to infinity, sum 2r less than n, 1 over 2j n minus 1 plus 2r to the power s, 1 over 4r squared minus 1. Well, where does this come from? This is the expansion coefficient evaluated plus 2r plus another term, c2 n to the minus 2, sum m equals n to infinity, 1 over m to the s, which is actually the am inserted here. Yeah, so I've put everything together based on this, right, which I've inserted for this term here. And then I've put here the corresponding am coefficients into here. And I'm going to call this one here S1, and this term here S2 for the sum 1 and the sum 2. And we now need to estimate S1 and S2 separately. And that works like this. So we rewrite S1 as the following thing. So S1 is, well, leave away the constant, 1 over n minus 1 to the s, sum 2r less than n, 1 over 4r squared minus 1, sum j from 1 to infinity, 1 over 2j plus 2r over n minus 1 to the power s. I've done nothing but take out the 1 over n minus 1 to the power s out of all of the other terms, and I've rearranged the sums that are down here. So now comes some classical analysis. So the first term here, even if the r runs from minus infinity to infinity, this would have a finite term, a finite sum, and so does this one. So because this one here, sum r from minus infinity to infinity, 1 over 4r squared minus 1 is equal to 2. Both sums are finite. Which is a good thing, because now this is less than infinity, this is some constant, this is less than infinity, so all of this together is just a constant, and we have the convergence rate that we wanted to have in this term up here in the S. All right, so we've treated the S1 term, and a similar thing can be done for the S2. Since this sum from 1 to infinity, 1 over j to the power s, so that's the zeta function of s, that's also less than infinity, we get from S2 that S2 looks like this, so it's n to the minus 2, sum m equals to n to infinity. I'm writing the term we have there a little bit more complicated, m to the s minus 2 times m to the 2. So then we can estimate n to the minus 2 sum m from n to infinity 1 over n to the s minus 2 m to the 2. That's possible because m is bigger than or equal to n. So I get an upper bound by inserting the smallest thing into the denominator. Then I can combine those two terms here. I can take out the m. So this is n to the minus s, and here I have sum m equals n to infinity 1 over m squared. And this we know is again less than infinity, so it's a constant. So the whole term is on the order of n to the minus s, which proves the desired result. And again, we've made the remarks already. It's a result that is actually good for Clenshaw-Curtis and for Gauss quadratures, because they also seem to beat the curse of dimensionality, at least in principle, judging from the convergence rates.